All right, so I'm going to do two examples for you, one in each video. This first one I'm going to do has to do with sound in a tube, a standing wave, a standing sound wave in a tube, okay? And it's going to involve an anti-symmetric boundary situation, all right? Now, what that means is I'm going to have a tube, so I'm going to draw my tube like this here. And if it's anti-symmetric, that means the ends are different. So the only way the ends can be on different and a tube is if one is closed and one is open, like this. Okay? Now, we need to know how long the tube is. All right, so the length of the tube is 1.8 meters. Okay? And what I want to know is what frequency corresponds to the fifth mode standing wave in the tube. Okay, so that means we're interested in n equal 5. Okay, so the fifth mode. Now, one way that I can write that, my question is like this. I can say we want to know f sub 5 equals what? Okay, and so that's a way of me indicating that this is the frequency for the fifth mode. Okay. Now we've got length. Length can tell us about the wavelength. Length gets us to wavelength. Then we've got frequency. So we're going to have to throw in velocity into the mix. Okay. So we're going to have here then that frequency times lambda is my velocity. Okay, so we have to know the velocity in this case. It's one of these 2 out of 3 kind of situations. Give me two numbers, I can tell you the third one. So between f, lambda, and v, I got to know at least 2 of those guys. So in a homework problem, it would tell you what the velocity is. Okay, it's generally going to be, 340, 343, 345, something like that. In reality, it depends on the pressure, the atmospheric pressure. It depends on the temperature a lot, and that sort of thing. But for our case, let's just make it straightforward and say 340 meters per second. Okay, so we'll go with that right there. All right, now back to f lambda equals v. Now, there are only certain frequencies and there are only certain wavelengths. So a lot of times when we've got a situation where there are these discrete values, in other words, only certain ones that can happen, we'll put a little sub n on there. Okay, and so if we want a frequency f sub n, that's going to be the velocity over lambda sub n. And in our particular situation, we want to know f5. So that's going to be v over lambda 5. So if we get lambda 5, then we can get f5. Okay, so let's work on lambda 5. All right, here we need to go with our equation of how we relate wavelength to overall length for an antisymmetric standing wave. So we're going to have here L is equal to 2n minus 1 lambda over 4. And let's put a little n on here. All right, so that n goes with the n on the inside, because that's what we're going to be doing here. All right, so n is 5. So we're going to have 2 times 5 minus 1 lambda 5 over 4. And that turns out to be 9/4 of lambda 5 is equal to L. Okay, rearrange that thing a little bit, and we're going to have that lambda 5 is 4/9 of L. Okay, let's get our number, because we know what L is already, 1.8 meters, and that turns out to be 0.8 meters, like that. Okay, now I'd like to kind of pause here just a little bit before we get back and find the actual frequency and talk about what does that mode of sound wave look like inside our pipe. Okay, and so in order to do that, let's do something here, let's look at a different mode, okay? So remember, with the anti-symmetric ones, you've got like half wavelengths and then a quarter dangling on there, okay? So we might have something like this. Here's a half wavelength, here's a half wavelength, and then a quarter. Okay, so that's our picture of the wavelength. And so a half wavelength, and a quarter. All right, now if we count it in terms of quarter wavelengths, I've got 1, 2, 3, 4, 5. Okay, so this is actually 5 quarter wavelengths. All right, 5 quarter wavelengths. Now, in our situation here with n equal 5, we need 9 quarter wavelengths. All right, so how do we do that? Well, what we're going to do first is we're going to subtract 1. So we go from 9 to 8. So 8 quarters. All right, 8 quarters is 4 halves. All right, so let's draw that in there. 1, 2, 3, 4, and there's my quarter. 1, 2, 3, 4, and my dangling quarter. Okay, now let's just double check that there's actually 9 of them there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9 quarters. There we go. Okay, so this n equals 5 standing wave in an antisymmetric pipe has a shape like this. So from here, then we could say, well, how many antinodes do we have? Well, we have 1, 2, 3, 4, 5 antinodes. How many nodes do we have? Well, we have 1, 2, 3, 4, 5, like that. Okay, and in these antisymmetric situations, you're always going to have the number of antinodes equal the number of nodes. That's just the way it works out. Okay, so let's get back after it. We know now that lambda is equal to 0.8. So we just want to plug that in. F5 is going to be 340 over 0.8. Okay, check out our units. Look at that. My meters go away. And we're left with 425 inverse seconds, but an inverse second is a hertz. Just like that. Okay. There we go. Now, there are a lot of variations on this, okay? So if you get your head around this, you watch this video, study the example carefully, all right, you're going to be in great shape because, to be honest, there's only so many things you can do, but there are a lot of different things you can do, all right? So it might be that you're given the frequency, maybe it tells you it's 425, and you know the length is 1.8, and you know the mode is n equals 5, all right, you might have to find the velocity. Okay, no problem, all right? You're just going to come back up here and use that, F lambda equals V. Okay, no problem. You might, in another scenario, be asked to find the value for n, okay? Given the frequency, given the length of the pipe, blah, 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 blah. Okay. How are you going to do that? Well, frequency and velocity are going to get you to wavelength. And then you'd come up here. All right. And wavelength with the length is going to get you to n. Okay. So there's different ways to do that. So study this example carefully. There's lots of variations, but they all come down to this kind of thing here, okay? Now, in the next video, I'll do an example involving some string, all right? And there we're going to bring in tension and the mass density of the string, okay? So you can see kind of how that works, all right?